So hello again. So now that we have a basic understanding of carrier transport, how carriers move in semiconductors out of equilibrium, we can talk about two other important processes, recombination and generation, beginning in this lecture with recombination. So let's consider first, what do we mean by equilibrium and non-equilibrium? Equilibrium we've discussed. We have these simple expressions that relate the equilibrium carrier concentration to the Fermi level, and we saw how to compute carrier concentrations in equilibrium. Now, out of equilibrium, there can be different ways in which we can introduce excess carriers. We might have added some excess electrons. We might have added some excess holes. Oftentimes, the process will add equal numbers of electrons and holes. Note that this excess carrier concentration can be positive. We can have more carriers than we did in equilibrium. It could also be negative. It's possible to remove carriers and have fewer carriers that are in equilibrium. So delta N and delta P can be either positive or negative. And the question that we want to discuss in this lecture is, how do these excess carrier concentrations vary with time? We know in equilibrium, the electron and hole densities are independent of time. So let's consider a p-type semiconductor in equilibrium, doped at 10 to the 17th in the extrinsic region. So the whole concentration in equilibrium is 10 to the 17th per cubic centimeter. The electron concentration then would be 10 to the 3rd per cubic centimeter. Okay, now let's introduce some excess carriers at time t equals 0. We're primarily going to be interested in the number of excess minority carriers, but let's assume that we've introduced an equal number of excess holes as well. We do that at time t equals 0, and we ask what happens. Now, intuitively, if we perturb a system, we expect the system to respond by trying to return to equilibrium. And oftentimes, this return to equilibrium is an exponential process. So we might guess that if we perturb this system by adding some excess carriers at time t equals 0, that the number of excess carriers will decay exponentially with time to get us back to equilibrium, and there will be some characteristic time. Okay, we're going to see that this is indeed the case, and we're going to try to understand what that characteristic time is. So that's our goal, is to understand that recombination time. Turns out that there are three different important and common ways that this recombination can occur. The first is band-to-band recombination, which usually gives off light. The second is a mechanism called Auger recombination. And the third is a mechanism that involves transitions through defects, which is called SRH, after the initials of the three people who wrote the first paper that described this, Shockley, Reed, and Hall. So let's discuss band-to-band or radiative recombination first. Here's my conduction band, here's my valence band, I have electrons and holes. An electron might drop down into the valence band and fill up a hole. After I've done that, there's one fewer electrons, there's one fewer holes. We'll say electrons have recombined, holes have recombined, and the energy has to go somewhere. In a band-to-band radiative process, the energy that was released in this process is given to a photon. Light is emitted with the wavelength of about the band gap, because electrons in the conduction band are near the bottom of the conduction band, holes in the valence band are near the top. This is a band-to-band radiative process. So it changes the concentration of electrons and the concentration of holes. And I can write down an equation. The change is negative because it's reducing their concentration. The change, in order for an electron and a hole to recombine, I have to have electrons and I have to have holes. So the rate at which they recombine is proportional to the product of both electrons and holes. The constant of proportionality is called B. People talk about the B coefficient of a semiconductor. That's an important material parameter for a semiconductor. And I have here NP minus Ni squared, so that in equilibrium, when NP is equal to Ni squared, the process will be 0, and there will be no There'll be no net recombination occurring. Okay. All right, so there's a concept now that isn't necessarily valid, but which is valid often and which greatly simplifies our analysis of these problems, and that's called low-level injection. So what do we mean by low-level injection? It means that when we inject excess carriers, say equal numbers of electrons and holes, that their concentration is small compared to the majority carrier concentration, but large compared to the minority carrier concentration. All right, so we can explain what that all means with an example. This is low-level injection in a p-type semiconductor. So let's say we have a p-type semiconductor. In equilibrium, it's doped with acceptors and produces a concentration of holes in equilibrium of 10 to the 17th per cubic centimeter. Using NP is equal to Ni squared, we see that we have an equilibrium number of minority carrier electrons, very small, 10 to the third, 14 orders of magnitude smaller than the hole concentration in this p-type semiconductor. Okay, now we introduce excess carriers, excess electrons and excess holes, and let's say we introduce equal amounts. Okay, let's say, for example, that we introduce 10 to the 8th excess carriers per square centimeter. You'll notice that that's 5 orders of magnitude bigger than the equilibrium minority electron concentration. So these excess carriers overwhelm the minority carriers that were there in equilibrium. But you'll also know that 10 to the 8th is 9 orders of magnitude smaller than the equilibrium hole concentration. So it's insignificant compared with the equilibrium hole concentration. That's what we mean by low-level injection. Low-level injection has negligible influence on the majority carriers. It has a huge influence on the minority carriers. Okay, so if we take a look at band-to-band radiative recombination in low-level injection in a p-type semiconductor, we can see what would happen. So if we've introduced the excess carriers, then the excess carriers overwhelm the carriers that were there in equilibrium, so the electron concentration is about equal to the excess carrier concentration. For the hole concentration, we had a large number of holes to begin with. We have an insignificant number of excess carriers. The hole concentration is about equal to the doping density, just what it was before the excess carriers were introduced. In my expression, I need to multiply n times p. So n times p is delta n for the electrons, Na for holes. That's much bigger than Ni squared, so I can neglect this minus Ni squared term. The result is that the change in electron concentration is basically the change in the excess carrier concentration. It's going to be minus B times Na times delta N. So the change is going to be proportional to delta N. I could lump parameters together and say it's just minus delta N over tau sub BB. Tau sub BB is just 1 over this B coefficient times Na. Tau sub BB is going to have the units of time. It's a characteristic time for this recombination process. Okay. All right, so we've taken our general expression, we've simplified it for low-level injection, and we have an expression that gives us this characteristic time, Na. So we now have a differential equation. That differential equation describes how these excess carriers will evolve over time. We solve a differential equation like this by guessing its solution. You've probably seen equations like this before, and you can guess that an exponential solution is going to satisfy this equation. Some constant times e to the minus t over this characteristic time. Plug this assumed solution into this expression, and you'll see that it works. So we have a solution. The excess carrier concentration decays exponentially with time. At time t equals 0, we have to get the number that we injected at t equals 0. So the excess carrier concentration is decaying exponentially with time, just as we had guessed that it probably would. If I plot delta t versus time, I get this characteristic exponential decay. All right, so that is one possible mechanism that carriers can recombine by. There are other ways that carriers can recombine, and we're just going to talk about some of the most important ones. So for example, let's assume that an electron and a hole recombine. They don't necessarily have to give up their excess energy to a photon. If it's an N-type semiconductor, there are a lot of electrons nearby. They might give up the energy to a nearby electron and kick it way up in the conduction band. When the energy is given to a second electron or a second carrier, we call the process an Auger process. Doesn't give off light, it's not a radiative process. The one I've just described is for an N-type semiconductor. It's proportional to the product of the number of electrons and number of holes, because electrons and holes are recombining, but it is also proportional again to the number of electrons, because I have to have an electron nearby in order to give it energy to. So this process is proportional to n squared p, and there's a constant c sub n here that describes the strength of this process. If I have a p-type semiconductor, electrons and holes can recombine in a p-type semiconductor, and then it would be important to have a nearby hole that the energy could be given to, and the hole would acquire extra energy instead of it being given to light. I have a minus Ni squared in each of these terms, so that in equilibrium, Np minus Ni squared goes to 0, and there's no effect in equilibrium. All right, so let's take a look at how this would play out in low-level injection in an N-type semiconductor. This is my general expression. I'm in an N-type semiconductor. I'm going to be dominated by this. Now I have an N-type semiconductor. So the electron concentration is going to be very large, given by the doping density. It won't be perturbed by the excess carriers. The minority hole concentration is going to be very small. They will be overwhelmed by the excess carriers. So the minority hole the hole concentration will be very closely equal to the excess carrier concentration. The product of the two is going to be much bigger than Ni squared, as long as I'm introducing an excess carrier concentration that's much bigger. Okay, so I can use these approximations for Np. In this relation, I can ignore the Ni squared, and I find that an expression for the rate of change of the minority hole concentration is equal to minus this constant c sub n times nd squared times delta p. Or I can lump things together into another characteristic time I'll call the Auger recombination time. That Auger recombination time is 1 over this Auger constant times nd squared, the doping density squared. So you can see that if the doping density gets very large, this nd squared could become very large, and this term could become important. There's one more recombination process that we'd like to discuss. This is very common in semiconductors like silicon. Another way that carriers can recombine is through an intermediate defect layer. So let's say that I have crystal defects, or I have impurity atoms. They might be heavy metals like copper, iron, or whatever, in the silicon in small quantities. Those defects tend to introduce electronic states in the forbidden gap. Now, these are electronic states that we don't want to be there. They're localized around these defects. The carrier current can't flow through these defects, but these defects can mediate recombination processes. An electron can drop down and be captured by a defect, and then it can drop down to the valence band and annihilate a hole. This would be called a defect-assisted recombination process, and it's important when the other processes aren't important. The energy that's released in this process tends to be released as thermal energy and just heats up the silicon lattice. Now, there is a theory that was worked out by Shockley, Reed, and Hall many years ago. The statistics of this recombination process are described by this equation. Again, you can see that there's an Np minus Ni squared to make sure that there is no net recombination under equilibrium conditions. And then there are some parameters here that are introduced in this expression. These characteristic times, tau n and tau p, are related to the concentration of these defects or traps, N sub T. And there's a constant of proportionality there. And the parameters N1 and N2, these have units of carrier density, and they tend to be carrier densities that under typical conditions have a magnitude that are close to Ni. So they're small carrier densities. Okay, so let's take a look. We're not going to attempt to derive this equation. You can see that derived in more advanced books, but let's take a look at that expression and let's apply it to low-level injection in a p-type semiconductor. So I have a p-type semiconductor, I have minority electrons. The minority electrons are going to be overwhelmed by the excess electrons. The holes in the p-type semiconductor are going to be not affected by the excess carriers, so the hole density will be Na. Np will be delta N times A, and it will be much bigger than Ni squared. Since I have a p-type material, P plus P1 will be much greater than N plus N1. In addition, since P1 tends to be on the order of Ni, P will be much greater than Ni. Carry that all through, and you'll find that under low-level injection in a p-type semiconductor, we find that dN dt is minus delta N over this characteristic time tau, which is related to the concentration of defects. So this is the recombination lifetime due to defect-assisted processes. It's 1 over the concentration of defects times this capture coefficient, which is a constant of proportionality that describes the processes. So just to summarize, we have described 3 different ways that electrons and holes can recombine: band-to-band, Auger, and Shockley-Reed-Hall, which is a defect-assisted process. We've shown that under low-level injection, they all can reduce to the same kind of differential equation. And we've shown that there is a characteristic time that describes this process, and we've derived that characteristic time in each of these 3 cases. So these are minority carrier lifetimes, and they're very important parameters in devices like solar cells or bipolar transistors that depend on minority carriers for their operation. Now, very often you'll find one process dominates and the other 2 can be neglected, but there are many conditions under which all of the processes are important. When they're all important, we add the rates of those processes together, so we add their inverses. You can see that that's the right thing to do. If I had a process that had a 2 microsecond lifetime and I had another process that had a 2 microsecond lifetime, if I had both processes occurring at the same time, I would not get a longer lifetime. I have to get a shorter lifetime. The way we get the shortest lifetime is by adding the inverses of those lifetimes. So the effective lifetime then will describe all of the processes that are important for that particular recombination process. So when are the various processes important? Well, the Auger processes become important when you have very heavily doped materials. So if you have a heavily doped material and it's a minority carrier device, you're worrying about the behavior of minority carriers, you should think about Auger recombination. Shockley-Reed-Hall recombination is important when there are a lot of defects present, or when there aren't many defects present, but when none of the other effects are important. Radiative recombination tends to only be important in direct gap semiconductors in which it is a strong process. So let's discuss that just a little bit, band-to-band recombination. Remember, we've discussed how this occurs in a direct gap semiconductor. An electron in the conduction band drops down and fills up a hole in the valence band. That's the recombination process that gives off light. That process has to conserve energy. The energy is given to the photon. That process also has to conserve not actual momentum, but crystal momentum, which behaves the same way. So the momentum of the electron to begin with was h bar k1. At the end, it was h bar k2. The difference in momentum is the momentum of the photon. It's actually an interesting little exercise I'd encourage you to try. If you try to compute the momentum of the photon, you'll find that it carries very little momentum. So the difference in momentum is about 0. This transition can take place vertically an electron from the conduction band can drop down to a state with the same wave vector at the top of the valence band. So these can be very strong recombination mechanisms in direct gap semiconductors. They are not strong in indirect gap semiconductors, and we can kind of suggest why here. In an indirect gap semiconductor, an electron in the bottom of the conduction band would recombine with a hole at the top of the valence band, but they would have different momentum to begin and end with. Well, we have to conserve energy, but in order to conserve momentum, we're going to need something that helps us conserve momentum in this process. That something else will be a lattice vibration. That lattice vibration will have some energy that has to be accounted for in conservation of energy, and conservation of momentum will take place because the difference between the initial momentum and the final momentum could be given to a photon, but there isn't much momentum in a photon, so that isn't going to help. So it's primarily going to be given to a lattice vibration or a quantized lattice vibration or a phonon. Now, to find the right lattice vibration with the right momentum to facilitate this process is going to be harder to do. In a direct gap transition, we don't need to look for lattice vibrations to help us satisfy momentum conservation. So the bottom line is going to be that this is going to be a much weaker process. We can generally ignore band-to-band recombination in indirect gap semiconductors, and it's the defect-assisted processes that become important. Okay, so we've discussed three types of recombination: band-to-band or radiative recombination. These are important in direct gap semiconductors, and we can put them to use in making semiconductor lasers and light-emitting diodes. Auger recombination becomes important when carrier densities are very high. So they can degrade the performance of devices like semiconductor lasers where the carrier densities are high. And Shockley-Reed-Hall recombination is the dominant process in indirect gap semiconductors because band-to-band recombination is improbable. In a direct gap semiconductor, if there are large concentrations of defects, then it could become important as well. All of the recombination processes were described by equations that had an NP minus NI squared term in them. That forces things to go to zero at equilibrium. So we had different descriptions for band-to-band, Auger, and Shockley-Reed-Hall. But notice that when NP is greater than NI squared, this is the situation we have been talking about. Then we have a net recombination, and that's why we've called this R. But it is possible for NP to be less than NI squared. Then R is negative. That's actually a generation process. You know, how would that look? We discussed the defect-assisted recombination this way. An electron in the conduction band hops down to a defect and then hops down to the valence band. In the process, we lose one electron in the conduction band and one hole in the valence band. That process releases thermal energy, and that occurs when NP is greater than NI squared. However, there's an inverse process. In fact, in all of these mechanisms, there's an inverse process. An electron in the valence band could hop up to that defect level, leaving behind a hole. And then it could hop from the defect up into the conduction band, creating an electron in the conduction band. This is going to require thermal energy to do this generation process. But this occurs when NP is less than NI squared. So the mechanisms that we have been talking about are actually both recombination and generation processes, depending on whether R is greater than 0 or less than 0. Okay, so just to summarize, when we introduce excess carriers into a semiconductor, the semiconductor responds by trying to restore equilibrium. It means removing those excess carriers. The simplest and most common case is when the perturbation decays exponentially in time with a characteristic time we call the minority carrier lifetime. That minority carrier lifetime is controlled by different types of physical processes. Depending on the particular semiconductor and maybe on how the semiconductor is doped, how carefully it's been prepared and what its concentration of defects are, those processes might be radiative, band-to-band processes, Auger processes, or defect-assisted processes, or all of those processes might be important at the same time. Now, in addition to these recombination processes, there are also some explicit generation processes. For example, if we shine light on a semiconductor, we generate electron-hole pairs. The subject of the next lecture then, and the final lecture in this unit, is a discussion of generation processes.